Good day, everyone. This is Anastasio G. Pantalion Jr. and welcome to my YouTube channel. In this video, we will be discussing the ideal regenerative cycle, the open feed water heater. So just sit down, relax, and enjoy learning. So in this setup, we have first the boiler or the steam generator. We have the turbine, and we have the condenser, two pumps, and an open feed water heater. So first, a steam coming from steam generator with P1 and T1 enters the turbine, expands to a pressure 2. But after the pressure 2, there is a mass of steam bleed off from the supply of steam, say M2, down to the open feed water heater here in order to heat your feed water going to the steam generator. And the remaining mass further expands at point 3, having the pressure 3, with a mass of 1 minus M2. Okay? Which means that a 1 kilogram enters the turbine. At some point 2, mass M2 is being taken off, and that is to be fed in the open feed water heater, and the remaining mass becomes 1 minus M2. Okay, this is your point 4, still 1 minus M2. This is your point 5, still 1 minus M2. However, at point 6, it becomes again 1, since 1 minus M2 plus M2 is being mixed and combined, wherein the target, okay, the main objective of the feed water heater is to heat the fluid at saturation fluid of pressure 2. Okay, we'll discuss that later. So this is 0.67. So this is what happens in the process of TS diagram. At point 1, okay, given a mass of 1, it enters the turbine, produces work. Turbine 1, 2. Now at point 2, a certain mass M2 is bleed off. Okay, M2 is bleed off. And further, after point 2, the mass further is utilized to produce work in another set of turbine and expands to point 3, where again it is working at work turbine 2, 3. So that's it. And the remaining mass goes to condenser, like this one. So this is the mass 1 minus M2. And condenses at saturated liquid at point 4. Okay. However, there's a need for a pump, another pump, in order for this open feed water heater not to produce any trouble. The pressure 2 must be equal to also to pressure 6 and pressure 5. And your main objective is that you have to pump the liquid, you apply work, pump 1 here. Okay, you apply work pump 1 at a constant volume to the pressure at which is equal to the pressure 2. Okay, this one is your pressure 1. This one is, let's extend the line, pressure 2. And this one is pressure 3. Okay, all throughout the process, pressure 2, pressure 6, this one is 6. Okay, this one is the saturated liquid, which is your target. That HF of pressure 6, which is equal to pressure 2. Okay, you apply work, the pump here, work pump. This is your 5. This one, this is your 5. Okay, hope you imagine that. And then, again, the resulting combination of the steam that is bleed off from pressure 2 and the uh, output of the pump is combined into such a mixture wherein it is rightly at saturated liquid at pressure 2. Okay, then again we'll pump this one. Okay, because there's another pump here, work pump 2, another application of pump, work pump 2, to the pressure of 7. Now pressure 7 is equal to pressure 1, since we are talking about isobaric process. Okay, take note, this is an isobaric process. The steam generator is an isobaric process. The turbine is an isentropic process. The condenser is isobaric process. The pumps are isovolumetric process. And the feed water heater is an isobaric process. Okay? So, what is this mass? How do you find this mass? First, you have to take note that we are only given P1 and T1. Okay? So, this would give you H1 and S1 through interpolation. Now, at point 2, you are only given pressure 2, but as you can see, the turbine is in an ideal situation. That is why we are assuming that S2 is just equal to S1 or isentropic. Now we take note, how do we determine the entropy or the state of the mass or the vapor if it is saturated or at still superheated region? First, we have to determine Sg at pressure 2. If this Sg at pressure 2 is greater than your S2, which is equal to your S1, then it is saturated, and you look at the saturated table. However, if your Sg at pressure 2 is lesser than S2, which is also equal to S1, then it is superheated. Okay? And you have to interpolate. So in this case, we find that in the drawing, okay, this is a saturated case. So therefore, you have to find the X. S2. So S2, which is equals to S1, is equals to SF at pressure 2 plus X, okay, X2 multiplied by SFG at pressure 2. Okay, these are all given in the table. Those you may find your X2. Therefore, your H2 becomes your H2 can be found by HF2 plus X2 times HFG2. Okay, hope we are clear with that. Another is at point 3. Okay, at point 3 is we have also an isentropic process where we see and we are assuming that everything is ideal in the process. So which means at pressure 3 given, but S3 is just equal to S2 because of isentropic process, which is also equal to S1. Okay, so if you know the process about whether the combined mixture or the fluid that leaves the turbine is saturated or superheated, you can do the same like this one. Okay, so however in this example it is plotted as saturated, so therefore you find your S uh, you can find your SX3 by merely saying that S2, which is equals to S1, is equals to SF3. What do you mean by that? Entropy of the fluid at pressure 3 plus X3 times SFG at pressure 3. Those you can find your X3. Then your H3 becomes HF3 plus X3 HFG3. Okay, you already have found your value of your enthalpy at point 3. Let's draw a line here. So at this point, the value of your 4 is pressure 4 is what? It is equal to pressure 3 because it is isobaric. However, your H4 is just equals to HF at pressure 4, which is also equal to your pressure 3. Okay? Now, here comes the volume. The volume 4 is equal to VF at pressure 4, which is equals to pressure 3. Okay? So we compute the work of the pump, first pump. This becomes, say, V4 times pressure 5. But what is pressure 5? Pressure 5 is just equals to pressure 2. Okay? Since we are talking about isobaric process of the feed water heater minus pressure 4, which is equals to pressure 3. Okay? You have your work, and therefore your H5 is just equal to H4 plus work pump 1. Okay? You might as well ask, Sir, what happens to the mass 1 minus M2? Does it affect the enthalpy? Of course it does. However, this will work only. The question will be answered later on in the calculation of the work. But hence, we are talking about enthalpy in kilojoules per kilogram. Then later on, we will use these enthalpies associated in the 1 minus M2. Okay? How about your 6.6? We have P6 is just equal to pressure 2. Okay? As you saw it in the diagram, isobaric process. However, your H6 is HF at pressure 6, which is also equal to pressure 2. As you can see here in your TS diagram. Okay? This is the optimum value of which your pumps will work. The enthalpy of your liquid must be at a saturated liquid. Otherwise, if it is at compressed state, you have to exert more work. But at a mixture state wherein there is a mass of vapor, your pump will be destroyed. So the optimum value must be at HF at pressure 6, which is also equal to pressure 2. As you can see here in your TS diagram, pressure 5, pressure 6, and pressure 2 are both equal. Okay? So we go to number 7. No, we have to find the V6 because we will be using pump. So V6 is VF at pressure 6, which is also equal to pressure 2. Okay, so work of the pump 2 is equal to V6 times pressure 7, which is also equal to pressure 1. Okay, as you can see, this is a steam turbine. It is an isobaric process. Pressure 6, which is also equal to pressure 2. Okay, those you have your work. Therefore, your 7 is H7 is just equals to H6 plus work of the pump 2. Okay, another one. Okay, let's draw here like that. Okay, so let's continue here. So how do we find the M2? Okay, of course, we saw it that everything has been given. H7 from 1 to, say, 1 to 7, all the enthalpy. Therefore, all you have to do is to draw a free body diagram of your uh, open feed water heater, this one. What goes in, goes out, energy in, energy out, conservation of mass, conservation of energy. What goes in? Okay, we have 1 minus M2 multiplied by H5. Okay, y minus 1 minus M2 because still 1 minus M2. Okay, what's left from here? Okay, as you remember, M2 has been bleed off, so the remaining mass to expand in the turbine at point 3 is 1 minus M2. It also enters the condenser at 1 minus M2 and still, and it goes out at the pump 1 minus M2 still. Okay, so that is why 1 minus M2. You have to write 1 minus M2. This one is M2 times H2. Okay? And the final output is, of course, the combination of M2 plus 1 minus M2 because by mass, okay, we have still H6 by combination Ca 1 is equals to M2 plus 1 minus M2. So therefore you cancel that. Okay, it becomes 1. Okay, this is your free body diagram. So what goes in goes out. H6 is equals to M2 H2 plus 1 minus M2 H5. Okay, so how do you find your M2? You have to distribute. Okay, so your M2 becomes H6 minus H5 over H2 minus H5. There you go. There you find your M2. Okay. Therefore, the work of the pump, of the first pump, becomes 1 minus M2 times the computed work of the pump, 1. Okay? Just be clear from that. At the initial calculation, we didn't include the 1 minus M2 because we want to have a unity of say kilojoules per kilogram. Now, when it comes to the application, the real work of the pump 1 is equal to 1 minus M2 because 1 minus M2 is the mass that enters in the pump. Okay? Or the power that enters in the pump times work of the pump 1. Okay? Work of the pump 2 is equals to, now it is all at unity 1. So we multiply that 1 times work of the pump 2. Now work of the turbine 1, 2. Okay. First, it expands at H1 minus H2 multiplied by the whole mass of 1. However, a steam is bled off. That is why work turbine 2, 3 becomes, okay, 1 minus M2. The steam that has been left or that is left to further expand in the turbine times H2 minus H3. Okay? Your heat rejection, okay, here, heat rejection, QR, your heat application here, okay, QR is equals to, what goes in? 1 minus M2, okay? So still 1 minus M2 times H3 minus H4, okay? Those your work turbine total is equals to work turbine 1, 2 plus work turbine 2, 3. Work pump total is equals to work pump 1 plus work pump 2. Your work net is equals to work turbine total minus work pump total. Therefore, your thermal efficiency of the entire cycle becomes work net over the heat that is needed to run the entire cycle. Okay? So I hope you enjoy learning and thank you for listening to this discussion. If you like the discussion, please hit the subscribe button. Thank you.